Hello, I'm Cheryl. In this problem, we're going to be trying to find the path of a heat-seeking particle when it starts at the point 1010, and we know that the temperature at any point xy is given by 400 minus 2x squared minus y squared. We're going to begin by getting a vector-valued function that represents the path of the particle. So that's going to be r of t equals x of t times my vector I plus y of t times my vector j. Now I want to see what the rate of change of this particle is, so I'm going to look at r prime. So r prime of t is x prime of t times vector I plus y prime of t times my vector j. Well, I also know that the gradient of my temperature function will give me the direction of maximum increase. So let's now take a look at the gradient of t. So the gradient of t at xy, to calculate this, we're going to take the partial of my function with respect to x. So that will be a minus 4x, and I'll multiply that by my vector I. Then I take the partial with respect to y, so that will be a minus 2y, and I multiply that by my vector j. Okay, now, the next thing I notice is that r prime of t has to be going in the same direction as my gradient function. So what that means is that this x prime of t has to be a constant multiple of minus 4x. All right, so all I have to do is make sure that the directions are the same. So I'll say that minus 4x equals some constant times x prime of t. And in the same way, minus 2y has to be equal to some constant times y prime of t. So minus 2y is going to equal some constant k times y prime of t. All right, so the next thing I'm going to do is just a little rewriting. I'll write that as minus 4x equals k times dx dt. And my second equation I'll write as minus 2y equals k times dy dt. And then I'll notice that I can solve each of these equations for dt over k. Now, how do I do that? Well, first of all, I'll divide both sides by k and multiply both sides by dt. So I'll end up with a dt over k on the left-hand side, and I'll also divide both sides by negative 4x. So I end up with dx over negative 4x. And in a similar way, I'll divide both sides by dt over k. So I've got dt over k, and divide both sides by negative 2y. So I have dy all over a negative 2y. Okay, what I notice from these two equations is that I can now say that dx over minus 4x is equal to dy all over minus 2y. And I have a differential equation that I can solve. So what I'll do is I'm going to integrate both sides. And on the left-hand side, I have a constant multiple of minus 1/4 that can be pulled out. And the integral of 1 over x dx is the natural log of the absolute value of x plus some constant. On the right-hand side, I have a minus 1/2 that I can pull out. And the integral of 1 over y dy is going to be the natural log of the absolute value of y. And again, I have a constant to add. Okay, so now I'm going to take and multiply both sides of my equation by negative 4. So that's going to leave me with the natural log of the absolute value of x equals 2 times the natural log of the absolute value of y. And remember, I've multiplied c1 by the negative 4 and c2 by the negative 4, but if I move it all over to one side of the equation, I just get another constant. So we'll call it C3. Okay, now I'm going to move the 2 natural log of y to the left-hand side of the equation. So I've got the natural log of the absolute value of x minus 2 times the natural log of the absolute value of y, and that still equals my constant. Now I'm going to use some log properties and write this as the natural log of the absolute value of x minus the natural log of the absolute value of y squared being equal to my constant. And I notice here that I've got the natural log of the absolute value of y squared. If I squared y, I'm guaranteed that it's positive, so I really don't need those absolute values in this case anymore. So when I rewrite using my log properties, I'll write this as the natural log of the absolute value of x all over y squared. And that equals my constant. Okay, so now I have a log equation. I'm going to exponentiate both sides, or in other words, change this into an exponential form. So because I'm using the natural log, this is the same thing as saying that e raised to that constant equals the absolute value of x all over y squared. Now, e raised to a constant is just a constant. So one more time, I'm going to introduce a constant, and this time I'm just going to use the letter c. That equals the absolute value of x all over y squared. Okay, so if I want to now, I can go ahead and rewrite this equation as cy squared equals the absolute value of x. And if you think about what this looks like, it's going to look like the top half of a parabola, a sideways opening parabola, in fact. And because I'm starting, if you think about a parabola that's opening sideways, I know that I'm eventually going to be hitting the point 0, 0. Well, why is that? Well, remember, I'm going towards the maximum temperature. And if I look back at my temperature function, the biggest number this is ever going to be is 400. And that's going to happen when x is 0 and y is 0. So I'm starting at 1010. And I'll be moving toward 0, 0. So what that tells me is that I'm on that upper half of my sideways parabola, which means I know that x is going to be positive as well. So c times y squared equals x. One last thing to do. I would like to figure out what that constant is for this particular problem. And I know I'm starting at the point 1010. So that means that c times 10 squared is going to equal 10. Or in other words, c times 100 equals 10, or c equals 10 over 100, which is 1/10. So my path that my particle is following is going to be 1/10 times y squared equals x. Or if you prefer, you could write it as y squared equals 10x. I hope that was helpful. Thanks.